All right, good morning, everyone. Welcome to the second day of the Haskell Symposium. We'll kick things off with a bang. Lennart Augustsson has agreed to tell us about a small compiler for Haskell.
All right, thank you. I will start with the demo, and I apologize if you were at my 5-minute talk at the Haskell Implementers Workshop a year ago, because the first 3 minutes of my talk will be the same as then. I will install MicroHs. So I've cloned the repo, and now we need to make the compiler. Oh, no, I need to, maybe I need to change directories. Yes, there, I made a compiler. So I could run this compiler, but I want to do a proper installation, so I will do make install, which will take that compiler I just produced there a moment ago and recompile from source so that we have the latest and greatest. And so when you download the repo, you get thank you. Okay, so it has recompiled the compiler. Now it's compiling the base package. So as I said, when you download the compiler, you get the C code you need to build the compiler. So the first thing there was just invoking the C compiler on the thing that you got when you did the download. Okay, so now it's installed, and we can try it. Let's see if it works. Yes, it does. Seems to work. Let's try something more interesting. Let's define I. So those who've forgotten how complex numbers work in Haskell, you say 0 is the real part and 1 is the imaginary part. So now we have I, and then we can take, say, I to the power of I. Does that look right? I don't know. Let's check. Is that equal to x of minus pi over 2? Yes, it is. Okay, it works. Isn't it amazing that when you raise I to the power of I, you get a real number? Okay. So you've seen how easy it is to install. Okay, so why is there another Haskell compiler? Does the world really need another Haskell compiler? I mean, there already is one. Or maybe there is 5. I'm not quite sure how many there are. Well, I don't care. So as you might have seen on the first slide, there was no affiliation there. That's because this is my hobby project. I do this in my spare time. So I think it's fun, so that's why I'm doing it. And maybe there is a need for another Haskell compiler because, I mean, GHC does all the things, and doing all the things take up a lot of space. But on the other hand, if you ever try to compile anything from, say, Hackage, you will discover, with something that's not GHC, you'll discover that everyone uses the GHC extensions. So, but anyway, so my goal when I set out to do this was that I wanted a compiler that could recompile itself in less than 10 seconds. I failed. But I could buy a new laptop. Yeah, so as I said, for my own entertainment mostly, but also I wanted to check how combinators work these days. I mean, back in the 80s, you could make things with combinators, and they worked. A lot of things have happened since then. I also wanted something that was fairly small so people could hack it if they want to. And so this MicroHs is a fairly small and very simple system. All you need is a C compiler. As you can see here, I run continuous integration on 32 and 64-bit Intel, 32 and 64-bit ARMS PowerPC, 32 and, no, only 64-bit RISC. I can't find a 32-bit one. And IBM S390. I've run it on a couple of microcontrollers. It's pretty easy. So a lot of the things in the runtime system is optional. All you really need is memory allocation. The rest of them, there are the ifs, defs, and the C code to say if your platform has standard I/O or if it has floating point and so on. And if you're running it on a microcontroller, you use the CFFI to do things. So, is it micro? So here is a comparison. So MHS is the micro Haskell compiler compiled with micro Haskell. GHMS is micro Haskell compiled with GHC, and GHC is GHC. So the binary for MHS is 450K when you compile it with itself. If you compile it with GHC, you can see there it's 24 megabytes. So it's somewhat larger. And I don't know how big GHC is. It was hard to figure out, maybe 120 megabytes. I looked around and added up some numbers because it loads up a lot of libraries. So something like that. MHS has, the source code is about 10,000 lines of Haskell and 6,000 lines of C code in the runtime system. For GHC, I think it's about 500,000 lines of Haskell and 130,000 lines of C and other things. We look at the last column first. When MHS recompiles itself, where the base library has already been compiled, it takes 12 seconds. That's why I think a new laptop will help. I can get those 2 seconds off. And GHC can compile MHS in 11.2 seconds, so it's almost as fast as GHC at compiling. But if I compile it with GHC and use that to recompile itself, then it takes 1.5 seconds. So, of course, GHC is a lot faster. But MHS is fast enough. I'm not going to go through this because it is a standard diagram of what things look like. The only reason I want to show you this is that there is a very small box for optimizations because there's only one. And there is nothing interesting. After you have desugared it, when you're down to basically lambda calculus, then you just turn it into combinators and you're good to go. There are no fancy tricks of any kind in this compiler. It's, in that case, in that respect, it's very reliable. I mean, there are no tricky optimizations that might kick in or not. It doesn't do anything. And the combinator stuff, that's taken more or less from David Turner's 1978 paper. I'll come back to what the one optimization is. So one little thing that might be unusual is that I use the same abstract syntax tree for terms and types and patterns and everything. And there's only a single type checker, so it used to type check terms, kind check types, and sort check kinds, because I don't have mushed types and kinds together. I'm still using the old-fashioned stratified way. These are the language extensions I've implemented, and they're not enough by far to compile all the GHC things, sadly. I might do some more. I probably will, because I want to compile some packages. Why aren't there more? Mostly because I'm lazy. And some of them I will never do, like template Haskell. I don't like template Haskell. The output of the compiler is just a combinator graph. So you can see the textual form up there. It's simple postfix notation. But it's generated as a C code in a byte array, so that you can give it to the C compiler. So when you compile a program, you have the runtime system written in C, and you have this enormous byte array that contains the combinators, and you give them both to the C compiler, and it will compile them and produce a binary. There's no pre-compiled object code for the runtime system or something like that. Every time you compile a program, it compiles the runtime system again. C compilers are so fast. Another 10,000 lines of C code, I mean, that's nothing. Okay, I'm going to skip all these things because they are, yeah. So here's the one optimization that I do. If there is a prefix of arguments in a recursive call that are the same, then I make a new auxiliary function for that. So this is typically something you might do for map. So you say map f is G, and then inside G you just recurse and you don't need to pass f again. And I'll come back to why this is an important optimization. It's not super important, but it helps a little. So I thought I'd spend a few minutes for the young people in the audience who might not have played with the combinators in the 80s, who barely had parents born in the 80s, probably. So here are the 3 combinators that you can use as a base for your. So I is the identity function, K is the constant function, it returns its first argument, and S is the thing, S, you can think of spread, it takes the X and it gives it to both F and G. And if you have these 3, you can take any lambda calculus term and turn it into SKI instead. So why would you want to do this? Well, if you've ever implemented any kind of language that has variables, you know that variables are a pain. You need to keep track of an environment. And if you have lambdas, you need to see what is captured, and you need closures, and it's just annoying. But with SKI, all the variables are gone. There are no more bound variables. There are only some primitives. There are SK and I, and then, I mean, there are some primitives to do integer addition and so on, and numbers. But there are no more variable bindings. They magically disappear, and you get the mess of combinators instead. How do you convert a lambda term to SK and I? Well, here is the little algorithm, usually called bracket abstraction. So if you have lambda x dot e, then you do this bracket abstract x from e. Okay, so if you abstract x from x, you get the identity combinator. If you abstract x from y and y is not x, then you get k of y, because you will be given an x later and you throw that away. And if it's an application, you just abstract x from both e1 and e2, and you put an s there, and it will take the x that will come later and give it to both sides. And if it's another lambda, you do another bracket abstraction. So super simple. And how do you compute with these? Well, if you view the combinator expression, it's best done as a graph, because if you do it as a graph, you'll get lazy evaluation. You will memorize things that you've done. So okay. So I write application nodes with an @ sign. So if you have an identity function applied to some graph, well, that should be identical to this graph. So unfortunately, you have to do something here. That application node might be shared. There might be many pointers into this. So you don't want to lose the sharing. So there are little indirection nodes that I write as a star. So that star means, okay, whatever was here is gone. You should use the thing where I point to. So this is what you get at the end. K combinator, 2 applications, K, first argument, second argument, okay. We point to the first argument, we drop the pointer to the second argument. Might be garbage, might be used by someone else, we don't know. We don't care, the garbage collector will fix that. Oh. S, F, and G, and X, okay. We overwrite this node with this new node that points to 2 new applications, F applied to X and G applied to X. And so for the Y combinator, that is the thing that you can use to make recursion. You have a special little clever rule that says if you have Y applied to F, you make an application where the function parts point to F and the argument points back to the application node itself. And if you haven't seen that before, you might want to go away and ponder it. And so how do you do reduction on this? Well, if this triangle is the whole graph, you start at the top is probably an application node. I mean, if it's not an application node, you're already done. And then you just follow the left pointers, the one that points to the function. And you follow it until you find a combinator or a primitive function, and that's where you do the reduction. And to make it more efficient, you keep a stack of pointers into this graph. So then when you've done a reduction down there, it's easy to find where to do the next reduction. You just pop up the stack a little bit. So that's how easy it is to evaluate combinators. Isn't it amazing? You'll see some C code in a moment too. So David Turner had more than S, K, and I in his 1978 paper, and so have I. And you can see with the little star out there which ones David had, and I've added a few more. This is a completely ad hoc set of combinations. Well, I took what David had, and then I sort of looked at the combinator output and so, oh, here is some stuff that seems to occur more than once. Let me make a new combinator for that. And I did that a couple of times, and if it sped up things, I kept it. If it didn't, then I didn't use that. For instance, you see K2, K3, K4, that sort of throws away different number of arguments. When I added K5, you didn't think that would hurt anything, but it got slower. So who knows? So in addition to these combinators that sort of do the shuffling of arguments, there are also some primitive functions like seek and arithmetic for the numeric types, the I/O. So I/O is done with, there are some combinators for the I/O, and they are interpreted by the runtime system. Catch and throw and stuff to do CFFI and things like that. So here's a cool thing that David Turner pointed out in his paper already, that if you have the, well, I can read, the second principal advantage is that the combinatory code turns out to have some remarkable self-optimizing properties, including that constant calculations are automatically moved outside of loops, and that the overhead of calling a user-defined function falls to 0 after the first occasion of its use. So if you see that function f of x is equal to 2 plus 3 plus x, so you might think, okay, well, an optimizing compiler should do that 2 plus 3 at compile time, do the constant folding. But there's no need with combinators. You produce this little graph int add with int add 2 and 3. And the first time you use the function, that thing int add 2, 3, that will be overwritten in the graph by 5, because that's the value of it. And you always overwrite function applications with their results in the graph. So the first time you use that function, that constant folding will happen. And this is very cool. I mean, for this, it's not so that interesting. But I will skip details of how you implement overloading. But if you remember how overloading is often implemented in Haskell, you pass a dictionary argument that has, say, all the methods for a number or whatever. And you pass that as the first argument. Now, the first time you use a function that has one of these dictionary arguments, there are lots of reductions you can do with only the first argument, only the dictionary. You can select the methods and so on. And that will happen. And the function application of the function to this dictionary argument will be overwritten by the thing where you have specialized it to that first argument. So the compiler doesn't need any thing that specializes for overloading. That just happens at runtime. The first time you execute something, poof, there you go. I will skip most of these because I want to show you. Let's define a function. Okay. That works, yes. Well, so I would like to show you now what this, well, let's check the type of ink. It's overloaded. So I would like to show you what this function looks like in combinator code. Unfortunately, as soon as I mention ink, it will default its argument to integer or whatever the defaults are set to. So you have to do a little trick. This is just to make the dictionary argument explicit. So now we can see. Now there's a secret thing that normal Haskells don't have. There is the combinator graph for this. It's pretty messy because it probably contains half the compiler because we haven't used the function, so there was no need to compile it fully. But if we do there is the actual code after you've used it. Let me make another one. Okay, here's the one specialized to int. Let's do it has specialized it down to what it should be. C is the flip. Since the number 1 came as the second argument to the plus, you have to flip. You could have an optimization for this also. Cool. Yeah.
But if you printed the polymorphic ink, like no, if you printed the ink specialized ink before applying it, it would already have been the much smaller, just not the smallest version, right?
Maybe. I mean, it's hard to tell when things happen with lazy evaluation. I only have 2 minutes, probably 1 minute now. So I just want to mention this. It doesn't do separate compilation. Instead, you can compile something like a package, and then you can save the internal state of the compiler, the cache it has of all compiled modules, to a file. And you can load that up if you want to. And that sort of works equally well as partial evaluation. And the reason you can do this is, well, I promised you some C code. Here are the combinators. Here are some I/O. The reason you can do this is that you can serialize anything here. Since functions are just this combinator graph, you can just take a point in the graph and say, okay, print this to a file, and it will keep the sharing and cycles and so on. Yeah. I have one more thing to show. Here is a microcontroller. Here's a battery. It's, oh, what happened? Did my microcontroller die just at this right moment? I saw it flash there for a moment. It's just a stupid USB. So it's signaling MicroHs, I think, in Morse code. You can see the Haskell code there that's running. It's a few bits missing that is doing the CFFI calls. So yes, it can run on micro things. Before ending, I want to have a rant about Hackage. I want to compile things on Hackage. There was 17,910 packages, and I just weeded out the ones that use template Haskell or GHC prim, and then there's 1,286 packages left. And I haven't looked at those. Those probably use a lot of GHC specific extensions as well. So it's hard work to keep up with GHC. You really need a lot of crap. And some good stuff. Yeah, I have a long list of things I'd like to do. And if you want to, maybe you already followed along and are running MicroHs already. Otherwise, here are the URLs. And
I have some syntax sugar very close to my heart. Do you implement lambda case?
You mean the syntactic extension? No, I hate it.
There's one combinator you didn't mention that I would love, par. Any chance that might make your compiler run in less than 12 seconds?
Yeah, so I have sort of a concurrent Haskell you can run here on it, so par should be possible, yeah.
Good.
So GHC has been accumulating all these extensions over time, and you can bootstrap GHC with earlier, like 2 versions before of GHC. So I'm wondering if there's a early version of GHC that you can compile with MicroHs.
Probably.
And whether you could basically bootstrap your way to something that only starts with MicroHs and then can...
Yeah. And if you want to bootstrap from nothing, I checked if Hugs, which you can get to from just C, if that could compile MicroHs, but it can't because I'm using pattern guards, and I'm not giving up pattern guards, and Hugs doesn't have that.
So you express this property where it like self-optimizes. Could that be extended to something that would basically implement memoization? So the code says, oh, the first time I see 3, I do the calculation. From then on, I know, at least for 3, what the answer is.
That's much more difficult.
So, yeah, thanks. Let's say you have a verified C compiler. How hard would it be to also like extend that to MicroHs to verify it?
Yeah.
So would it be possible, or like?
Possible. I mean, yes, of course it's possible. I'm not going to do it, but if someone else wants to do it.
Because you say it's minimal in that sense. So
Yeah.
It sounds to me much easier to do it there.
Yes, I mean,
GHC.
I think you have a better chance than with GHC.
Okay, yeah. Thanks.
Thanks for a delightful talk. It's clear you had a lot of fun making this. That's awesome. There was a similar experience from the racket world where Matthew Flatt recently had a ton of fun implementing something called Zo, which is a tiny racket. But he did it because he then went and replaced like gobs and gobs and gobs of makefiles with Zo instead. So completely making the build system on all the different platforms for. So I wonder if something like that might be a role that MicroHs might play in the GHC world in a different way someday that, you know, yeah.
I don't know and I don't care.